If you take those big models, you're running into the problem like you need already compute power, you need infrastructure, you need ML ops, you need a whole department to actually make use of those models. Not many people have that, right? Especially those companies that it's most useful for.
You're listening to Gradient Descent, a show about machine learning in the real world, and I'm your host, Lucas Biewald. Today, I'm talking to Johannes Otterbach. He was originally a quantum physicist and then went into machine learning, and he's currently VP of Machine Learning at Merantix Momentum. Merantix is a really interesting company that develops all sorts of machine learning applications for customers, small and large, and then really deploys them into these real world systems and hands them off. So we really get into real world applications of ML in factories and other places, the tooling required to make machine learning work, and also how to do smooth handoffs so that customers are actually successful in that transition. This is a really interesting conversation, and I hope you enjoy it. My first question for you is looking at your resume. You're one in the long line of people that kind of moved from physics into machine learning. I'd love to hear what that journey was like. Like studying quantum physics, and I think you worked on a little bit of like quantum engineering or quantum computing, right? And
Mm-hmm.
then now you do machine learning. How did that happen?
Yeah, that's a great question. I think initially I was super excited about physics because physics I just saw as something to understand the world, and I'm really like excited about understanding how things work and taking things apart to put it back together. And that's always drawn me to physics rather than engineering. And was on track to just like do a career in physics. And then AlexNet came out, and the ImageNet challenge happened. And I'm like, holy crap, there is something really cool happening. And it's always funny to tell people like I did my PhD before ImageNet was a thing because that makes me really old. But it's kind of an exciting time. And so when I heard that, I was like, well, I want to reconsider my career as a physicist anyway at that point, and looked into what this AlexNet was about and the ImageNet challenge, and discovered this whole field of data science and big data that was starting off at that time. And that's a very natural transition for a physicist because we're good at statistics, we're good at modeling, we like math. And then I fell in love with this big data science. And since then, I've been continuously driving at understanding the language of data, and ML is just like an expression of that language, and that's why I fell in love with it, and now I'm here.
And you did do some work in quantum computing, is that right?
Mm-hmm.
Do you think that quantum computing has anything to apply to ML, or do you think like ML has anything to apply to quantum computing? How do you think
Mm-hmm.
about that?
That's a great question. I think it's mutually beneficial, and I see there will be a convergence of those two fields in the near future. Um, there's four different quadrants that we can talk about. We have like classical and quantum in terms of engineering and in terms of data. So you have quantum data and classical data, and you have quantum algorithms and classical algorithms. And so you can actually start to think in those four quadrants. And I think that right now we see that a lot of effort is being put into using quantum algorithms to classical data. And that I think is actually potentially the wrong way to think about it. We should always think about like quantum algorithms for quantum data and maybe classical algorithms for classical data. And these cross fields are a little bit more complicated to solve. And there I think is like cross fertilization is going to be happening. And
What
the
is quantum data?
quantum data is essentially data that comes out of quantum states. Like I don't know how deep you are into quantum computing, but typically in quantum computing we don't talk about definite outcomes in a way, but we're describing systems by wave functions, which are naively speaking the square root of probabilities, quote
Mhm.
unquote. Like don't take this too serious. And so what you get with this is essentially expressions through quantum data, which has a phase and an amplitude. And if you start measuring this, you get a lot of complex numbers, you get various different types of phenomena. And those data typically take an exponential time to read out into classical states. When you have a quantum state and you want to completely express that quantum state in classical data, you get an exponential overhead in storage.
But what's a
So you,
situation in the real world where I
Mhm.
would have quantum data? Like I can imagine how these quantum computers produce that, but when would I be collecting quantum data?
When you actually deal with quantum systems, right? If you want to start to understand molecules, for example, very deep interactions of molecular properties, they are ruled by quantum rules. And so if you want to simulate molecules, you rather want to do it in quantum space than in classical space. That's really the way to go. And so that's why modern or early stage today's quantum computers are more simulators of other quantum systems. So you use these computers to simulate quantum systems that you want to study under very, very controlled fashions. And then you deal with quantum data at that point.
And are we actually able to simulate quantum systems in a useful way? Because, I have experience with kind of classical mechanics systems, and the simulations seem to break down very quickly. So I can only imagine that the quantum simulations are much harder and probably harder to make accurate.
We are getting really good results, and like a lot of quantum experimental physics is essentially doing that. We have toy models that we use in order to validate our mathematical theories. A good example is a field that I worked in back in the past, which is quantum optics, where we have a lot of laser fields and single atoms, and we start to put them together in a certain fashion in these laser fields so that we can simulate materials that we really have hard time understanding, like, for example, high temperature superconductivity. We have certain types of mathematical models, statistical models, that we think about, like how these things can come across or can come about. And then in order to study the effects of these models, we use a very clean system that we have a high level of control for and try to simulate those mathematical models and see if those models then give rise to these phenomena that we see, for example, in these materials that have high temperature superconductivity. So we use a much simpler system to simulate a much more complex system in order to probe our understanding of the physical laws here in this case.
Is there applications of ML to that? I feel like we've talked on this show
Mm-hmm.
to some chemists in different fields, and they've been sort of using ML maybe to approximate these kinds of interactions. Is that
Mm-hmm.
is that an interesting field to you?
I think that's an interesting field to me. But actually, I think I'm much more excited about a completely different avenue of applying ML to quantum systems. If you think about building a quantum computer, you have a lot of different qubits. These are like the atomic units. You have bits in a computer, a classic computer. You have qubits in a quantum computer. To use and address these qubits, we have to very, very meticulously control those qubits in order to really make them do what we want, because you cannot just flip a switch from 0 to 1, but you have to control everything between 0 and 1. It's a very, very analogous computer, like an analog computer to a certain extent. And in order to control these kind of systems, I think here is where ML comes into play, because you can use, for example, reinforcement learning techniques to do optimal control of these quantum gates in order to facilitate those 2 qubit interactions or 3 qubit interactions in order to get a high fidelity quantum computer. And I think that might be the one of the early applications of ML to quantum systems and to quantum computers. And my firm belief is that we probably need like machine learning techniques, modern machine learning techniques, in order to scale quantum computers to the sizes that they are actually useful.
Interesting. I feel like I've met a number of people in machine learning that kind of feel like they're refugees from quantum computing. Like they felt like it didn't really have a path to real world applications and kind of moved into machine learning. And when
Mm-hmm.
I saw your resume, I wondered if you were one of those people. But it sounds like you're pretty optimistic about the future of quantum computing.
Yeah, I think that the question is on which time scale, right? Quantum computer is still very nascent, and I feel that quantum computing will go through like the same kind of winters that machine learning went through a while. When this will happen, I don't know, but we will see these kind of winters coming out. I, in my lifetime, want to see some more impact on a shorter term timescale. And I think that machine learning is the right path for that. And I actually don't think that I shut the door. At some point, I want to do a bit of quantum computing again, but maybe take my ML knowledge to quantum systems in order to facilitate some better approaches to do that. But right now, quantum computing is very much at the hardware level, and I'm a software guy.
Cool. Well, tell me about your work at Merantix. Maybe we could start with what Merantix is and what you work on there.
Yeah, sure. Merantix is a super cool construct, actually. We have like 2 separate units. We have Merantix Momentum, and we have Merantix Studio, which is the overarching company. Merantix Studio is actually a venture studio that focuses on deep tech in Berlin. The idea here is that we have like pre-vetted industry cases where we then look for what we call entrepreneurs in residence that want to work on certain critical domains that we deem necessary in order to bring AI into broad adoption outside of just B2C businesses. And the venture studio looks at those different use cases, then starts to seed an entrepreneur in residence, lets them have like 6 months to a year of like vetting the use case and then build up their venture. So Merentix Momentum is one of these special ventures because we are actually not an independent venture. We are a 100% subsidiary of Merentix Studio. And we are focusing on these use cases where it's not big enough to actually build a venture by itself, but actually still need help for certain domains where we try to focus on use cases of clients that have actual problems to see how can we actually apply ML techniques and ML deployment techniques and ML ops to help those customers in need. Classic example are, for example, visual quality control manufacturers. They have no IT stack, they have no IT system, but they have very hard visual quality control problems. So building a vision classifier based on a convolutional network just offers itself. We built that for them, make sure that it's actually scalable, and then also help them put it into production close to the sensors. You can't build an own venture around it, but Merentix Momentum can actually do it. And that's what we're here for. And so within that ecosystem,
I guess why do you think you can't build a venture around that? I mean, it seems like that would be pretty useful to a lot of people.
I think the question is how quick do you gain significant market cap, right? I think eventually you can build a venture around this, but I think the adoption is not big enough yet in order to build your own venture around it. And in a way, Merentix Momentum is the venture that can actually do that because we're in that sense, we are a professional services department where we go in and say like, hey, you have a problem. You want to have a one-off machine learning model. We can help you get there. And that's what we're doing. And so that's kind of the venture around that. But like you wouldn't build a venture to just go out and do visual quality control for company X, Y, or Z.
So how does it work? I mean, I would think that doing this kind of thing for customers would be very hard to scope, right? Because I feel like one of the challenges of machine learning is you don't really know in advance how well a particular application is going to work. And then downstream from that, it would probably be hard for customers to estimate how well different levels of quality of the model would really impact their business. So like, how do you make sure that a company is going to be happy at the end of one of these engagements, or do you just view it as sort of an experiment?
That's a really great question. And I think that we are getting some tractions on that. So the key here is to work early with customers to understand their needs. We really have like very intense engagements before we start our work to make sure, is the use case actually solvable? How big is the challenge? What kind of data challenges do we meet? Which kind of approaches would we actually take, and really take the customer on a journey before we really say like, now we start engaging. And the way that we approach this is like a staged approach where we have more like individual workshops, which we call the AI Hub, which is a pre-study to an actual work engagement, implementation engagement, so that the customer understands what can be achieved with which data, with which kind of effort. And then we start the implementation work. And then when implementation work comes, of course, it's a professional services. There's always a little bit of security and risk, but we already mitigated the risk significantly. And often it comes out that some problems are not solvable, and then we go to like a different type of model, which I'm actually working at.
What type of model is that? You work on unsolvable problems? Is that what I just heard you say?
No, not unsolvable problems, but problems that you cannot just do in like a client engagement, right?
I see.
There's a different funding strategy that also exists in the US to a certain extent, but much more so in Germany and Europe, which is publicly funded research projects. The German state or the federal government is interested in solving certain types of problems that are industry spanning, but they're too hard for just a single company to just work on it because you have to bring many different domain experts together. And so they fund consortial research, which is typically like 4 to 10 partners, where you have application partners that bring their challenges, problems, and data sets with them. Then you have academic partners that bring in academic state-of-the-art research facilities. And then you also have professional service company like us who really understand deployment models, deep tech industry applications. How do you make machine learning models robust in that? And you engage in translational transfer research to use the academic results to apply to industry problems. Once you solve that, then you have enough data to actually then bring it to a client engagement in a B2B relationship.
Can you talk about some of the things you're working on specifically?
Specifically, yeah, we have a bunch of research projects that are going on with big manufacturers and automotives in Germany. We just are about to finish a project on self-driving cars, autonomous vehicles. Very classic use case for Germany, I would say. And here the idea really is that car manufacturers do not really understand all the details that are involved in building a, for example, segmentation map for optical flow application, but they are very, very good in understanding functional safety regards. And so really bringing those two domains together of saying like, we need self-driving cars, autonomous vehicles, but we don't know how to build the segmentation models. We need this domain expertise. And we said, we know how to build those segmentation models, but we don't know actually what are the safety critical features and how do we bring those together. And that was a research project that we worked at.
That's cool. So you're doing segmentation on vision, basically from vehicles?
Yep. So there's computer vision is one of them. We were investigating synthetic data sets where you have essentially rendered data set in order to pre-train those models. Optical flow detection, bounding box detection, person detection. These are some classic models. We also have other research projects that are much more going into optimization problems, where you need to understand how manufacturing pipelines actually look like. Cool example. I unfortunately cannot name the company name, but like imagine you have a critical element for building a car seat. There's like metal bars. And these metal bars, they are, funnily enough, going through like 50 different manufacturing steps. Right? It sounds crazy, but it's actually true. Those 50 manufacturing steps are distributed over 10 different factories of 5 different just-in-time partners.
Wow. Can you give me some examples of what these steps might be? It's hard to picture 50 steps in a metal
It's
bar.
like the raw metal forming to like the raw rod, then the first processing to bring it to the right rod, then you do chroming of the rod, then you start the first bending iteration, then you rechrome, refinish, do the second bending, do the next step, and so on until it's in the right shape.
Wow,
so
amazing.
Like there's a lot of this stuff. Yeah, I didn't know about that either, and it's pretty crazy. And what happens now is that in your manufacturing process, a mistake happens at step number 10. You don't notice that mistake until step number 15, when your metal bar is a little bit outside of specifications. So typically what happens is that now you take this whole batch and you put it to scrap metal and start from scratch. However, the challenge now is like, can you do something in step number 20, maybe, that you can bring that rod back into specification so that at process step 30, 40, 50, it fits again back into specifications. And now you can imagine this is like a very high dimensional optimization problem with a very sparse reward signal. So classic optimization problem. That's kind of research projects that we're working at. And now is the question, like, what kind of techniques in the field of ML can we use and transfer to those kind of problems? And what kind of data do we actually need for that?
So what would be the choice here? Like, what would you do differently at, say, step 20 that might make it useful in the end?
We have to find what are the kind of levers, right? And there is like different types of process step. Maybe you don't heat it up as much, or you overbend it a little bit into one direction and rebend in the other direction. Maybe you do a refinishing at some point. These are like all the levels that we have, and we have to explore like what is the actual problem. And here you start to see the devils in the details. What are actually the effects that matter? Like it's causal inference problem, it's a Bayesian learning problem. We don't know yet because we just started this project. So I wish I knew the answer, but then I would have already published something around that.
Well, so you're just working on a totally wide range of machine learning applications in the real world.
That's right.
You must be building a really interesting set of tools to make this possible. Can you talk about the stuff that you're building that works across all of these different applications?
Yeah, no, that's a super question, because I think that's one of the things that we do extremely well, and we have a lot of fun doing that. Maybe let's start a little bit back, because one of the challenges that we have, of course, being in Europe, lots of companies have very, very little trust in cloud deployments here. So you have to start with the customer and saying like, what happens here? And one of the things that people are super afraid of is vendor lock-in. So we have to build a tool stack that really is cloud agnostic. So we can deploy it like on-prem, we can do it on GCP, AWS, Azure, you name it, whatever it is. So that's the first prerogative. We need to understand like how to build a stack that's completely agnostic of the underlying cloud. And so in order to do that, we start, of course, building stuff on Terraform and Kubernetes. So we do extensive use of those systems to automate a lot of deployment tasks. So infrastructure as code. Now, once you start going into like all of these files, you're getting fairly quickly lost in them because like these configuration files start to become very, very complicated. So we started to build tools to automate how we actually write deployment files. So we have an internal tool, which we also, funnily enough, call DevTool, that essentially is nothing else than building very specifically pre-programmed template files in order to spin up complete deployments automatically. And so we're completely independent of the actual underlying cloud because we can just spin up the templates of a full deployment cluster. And on top of that, we can then start using all kinds of other tools that we need in these clusters, what we deploy. We are typically heavily reliant on Dockers. So we build a Docker file that we can then deploy on a pod that we command using Kubernetes or Terraform. For the deployments, then we use Seldon. We use a Flight pipeline to automate complete learning pipelines. CI/CD in that loop is done with Flight. And right now we still have Cloud Build, but we're already thinking about like how to get that out of the loop. So we're trying to be really, really cloud agnostic and build like a whole stack ecosystem on this modern ML tools.
And is this stack I guess you're deploying into a customer's production environment? Does this include training, or is it just for running a model for the customer?
So that really depends on what the customer actually wants. We are right now, we are targeting towards ML Ops level 2. I think that's what Google calls it. We are not quite there yet. But so right now we still have like a split between manually triggering a retraining that we do internally using our stack in like the cloud or on their on-premise system. And then also having a separate manual step to actually deploy it into production. And we're doing both of them. Like we can actually do it, the deployment step and the retraining step using all of our infrastructure. And the target really doesn't matter. Because we build a cloud agnostic, we can, for example, do a retraining on our internal cloud, which we mostly use GCP right now for us. But if the customer wants to have the model in their production stack, we train it on our cloud and then move it to their production stack on-prem.
And I guess, what have you learned building these tools? I mean, it sounds like you're making the stuff, you're deploying it. There's many people trying to build these things. What have been the kind of lessons actually when these things get deployed into customers' systems?
That is really, really hard still to do.
Why is it hard? Because conceptually it's simple. Like, what actually really makes it hard?
It's actually not that hard if customers are okay with using cloud deployments. I think what makes it hard is if they're using on-prem in their own stack, because then suddenly the tools are not yet at that point where you can just abstract away every kind of sysadmin. You're always having this touch point between how is that hardware actually managed and how can you deploy it. As soon as you have a Kubernetes cluster installed on premise, you're probably fine again. But until you get there, you cannot abstract that system away. And then you're also getting these realities of the business that you sometimes have to deal with IoT devices. And then deploying stuff onto IoT, that's really not there yet. And I think the tools are falling short on that end, but I think that's just a matter of time until we have more tools that are ready for IoT deployments.
How do you think about monitoring the system in production? I'd imagine these things could be somewhat mission critical, but I noticed you didn't really mention production monitoring. How do you think about that?
I think it's very important, and we do it. We are not necessarily deploying extremely mission critical systems right now, so that's what we haven't done yet. I think we're getting there soon. But right now, it's mostly just like measuring uptime and making sure that the stack doesn't fold under load. So it's just like the standard production monitoring that is just Grafana, load testing, throughput measurements, and these kind of things, not necessarily decision making and auditing trails in that regard. So it's more like a standard site reliability monitoring in that sense. And that can be automated fairly easily using Grafana or any other monitoring tool that you like. Got
it. I thought you might want to talk about some of the tools that you've developed, like Squirrel and Parrot and Chameleon. Can you describe what these are?
Yeah, that's really cool. Like, my personal favorite right now is Scroll, just because we're just like about to launch it and release it out into the world, which is super fascinating. The goal here is that if you take a look into the ecosystem, we are very, very good at building ML models for training on single GPUs. But as soon as anybody encountered for the first time trying to deal with multiple GPUs, you're getting into big problems. And many frameworks have come across that are actually helping you to distribute a model, but nobody has really thought about like how do you distribute the data.
Yeah.
And there are not many frameworks out there. There's a few things that we have looked at that are trying to solve that, and the ecosystem is getting bigger. But we are now decided we want to go into like a place where we can really make data loading on distributed systems as easy as possible. It doesn't need to be only for deep learning, but it can be for a lot of different things. Um, and on top of that, also build in potential access control levels, right? Like you want to pull that one from this bucket, the next one from that bucket, the third one from this bucket, and make sure that you mix and match this very well. And that's what Skrill is really about, to make data access and data storage and data writing super, super simple as you can do it by just abstracting away the file system. It can be on a cloud, it can be on local, it can just be pulled from the internet, and it should be easy to integrate in any kind of framework. And that's really what we're doing here.
And your plan is to make this open source?
The idea is to make this open source. Exactly.
Cool. And I guess, do you have like a preference of like other open source tooling? Like, do you guys kind of standardize on your like ML framework and things like that?
Mm-hmm.
Like, what's sort of your set of tools that you would typically like to use?
I mean, we of course also standardizing as much as we can. You can imagine like having many customers, you want to have standardized tools. So
Totally.
our standard framework is PyTorch. That's what we're doing internally for training these models. We're also betting a lot of PyTorch Lightning as an easy framework. We're also using Hydra, that's developed by Facebook as a interface and an entry point into those systems.
Why did you pick PyTorch Lightning? What did you like about that?
I think the idea here is that it really abstracts away much of what ML training frameworks have to do. You're writing a data loader, you're having an optimizer, you're having a training loop, and you have a logger. And typically, when you just look at typical GitHub repositories, everybody writes for batch in data loader. Do all of these kind of things. It's a very repetitive code. Like just abstract this away, use some software engineering so it's robust, and then you can go with that, right? It's especially important if you're doing production models where you just have to retrain and you need to be stable on that. Software maintenance is, I think, one of those things that is not really in the academic ML community, which comes as a surprise to me because a field that is coming out of the engineering should value good code qualities a little bit more, I feel. So we have to do it ourselves. And so use tools that make maintenance and debugging of machine learning models easier. And so frameworks are the way to go for that, because you don't want to build it yourself if the community can help you maintain the systems.
Do you also use PyTorch to run the models in production? I know some people will kind of change the format or like do something to the model before it's deployed. Do you just like load up the model as serialized from PyTorch, or do you do anything special there?
No, we typically deserialize it from PyTorch directly because right now our modus is to ship Dockers around the world.
Mm-hmm.
I think eventually we probably, for certain applications, need to go into like a more standardized frameworks like ONNX or something like that. That will change the game potentially, but right now we are still using the binary Docker.
Where do you see gaps in the tooling right now? As someone that likes to make and sell ML tools, like what I guess what parts of the stack feel mature and what parts feel broken?
Um, what feels broken to me is that you have to plug many systems into many systems. And that feels a little bit sad because that makes it really hard sometimes and to stay abreast of the edge. I don't think that there's anything lacking in the community right now. I more feel like the problem is that too many people are building too many tools instead of just like coming together and take one tool and bring it to the next level. The thing that then happens is that people try to be different from others instead of making one tool that solves a lot of problems. Counterexample where this worked really well is in the data science world, right? You just need 2 or 3 libraries in the data science world, which is scikit-learn, NumPy, and pandas, and you're set. If you're going into like MLOps domain, like I don't know how many tools out there. You probably know better than me, and it's just I wonder sometimes why. Right?
Yeah, that's fair. I mean, I definitely think there's always a moment where there's like an explosion of ideas and tools, and then things start to standardize for sure. And I think we're
Hmm.
still at that explosion
I
stage,
think
but
so.
that's what makes it interesting to, to be in this world right now.
I agree. I think that there's a lot of abstractions we haven't figured out, like, for example, deployment to IoT. What I'm super curious about that I haven't seen much development until recently is how do you deploy models in heterogeneous environments? How
Hmm.
do you train on heterogeneous environments? I think there's still like a lot of ML tooling that needs to get better. Not everybody has like a huge data center of homogeneous hardware. So how do we deploy models or train models on heterogeneous hardware?
I guess another question I have is, how do you hand off these models to a customer? Like you say, you give them like a Docker, but if they want to kind of keep iterating on a model, like once they've taken it from you, are they able to do that? Or how do you think about that? Because it does sort of feel like machine learning projects are never really complete, if you know what I mean.
Yeah, no, I understand what you're saying. It's like it depends on the customer. I don't think that there's a one rule fits all. Some customers just like come back and say like, hey, we need retraining or we need a fresh up, and can you do that for us because they don't have an IT department. Some people want to jumpstart their IT department. They say like, okay, we know machine learning is the future. We don't have an IT department yet, but like maybe engage with you and you help us to jumpstart the engine, right? And then they start continuing in that code. It's always, of course, a conversation because it's also tricky for us to say like, hey, we're offering our expertise, we put in a lot of sweat, tears, and blood, and then you take it to the next level. That's always sad as well. So it's always a tricky conversation, but we're happy to help people, and I ultimately think that everyone benefits if the community just grows.
I guess another question I wanted to ask you about is you've written a few thought pieces on AI. I don't know if you have a favorite, but I think one interesting one was your writing on the impact of NLP models on the real world. If you could like summarize for people who haven't read it, my perspective is that in a way the NLP field seems to be doing like a whole bunch of very amazing things. And I know people argue about like, is this like real intelligence or not? Or like, how much does it really matter? But I guess from my perspective as like a technologist and enthusiast, I kind of can't believe how good text generation has got in some
Mhm.
sense. And yet I think the impact to me is smaller than I would have imagined from like how impressive the demos look. I
Mhm.
don't know how you feel about that.
No, I see your point, and I think that is exactly the reason why I like working where I am, because it's right in the middle of driving the adoption of modern AI techniques. I think the reason why you feel the impact is not as big as it could have been or should have been is that it's really, really hard to bring technology like that to people who are not technologists like us. And that's really the challenge here. Like you have to bridge that gap, and there is this early adopter gap, and that needs to be bridged, and we are not there yet. I'm also with you. I don't really want to get into this philosophical debate. Is it intelligent? Is it conscious, or whatever it is? It's like it's useful technology. Let's bring it to the people and have them have a better life with it, right? Let's solve some problems with that, and that's maybe like the philosophical side. The practical side is if you take those big models, you're running into the problem like you need already compute power, you need infrastructure, you need ML ops, you need a whole department to actually make use of those models. Not many people have that, right? Especially those companies that it's most useful for. Take, for example, news outlets or media outlets. They are completely focused on a very different problem. They don't have technologists that just like take a GPT-2 or even a GPT-3 size model to put it into a production and then figure out the use cases, right? Like that's just like not how the economics of these companies work. And so bringing it to those people is really hard. And that I think is the reason why we don't see that impact yet. And it's going to come, but it's still going to take a few years.
What do you think are the next things that we're going to notice just as like consumers from the impact of these more powerful NLP models?
I do think that a lot of stuff that will come is improvements in search. I think that the thickness that we get from like similarity clustering is significant, and we just need to figure out like how to adopt that into real worlds, right? If you just run GPT-3 size models. The search is slow, so we just need to do some improvements on that. But I do think that we see a re-ranking on that front. I also think that a lot of automation will happen for automated text generation. And that's a positive thing. Like, I don't know how much time you spend on emails. I certainly do a lot, and you probably do too. And it would be nice to just automate some of that stuff away. I also talked to several customers in Germany that have this funky problem where they're in like a logistics space. And logistics is a very old school domain where you get very free form order forms. And there are armadas of people that just do nothing else than taking those emails that are just free floating written and turn them into structured text by just manually copy pasting into a structured field. Sounds easy. It's not. It's a very, very hard NLP task. Once we bring these big models into that realm, I think there will be a lot of automation for the better. And so I do think there's a lot of potential. I'm very excited about the future of those models.
Cool. You also wrote an article on AI and regulation I wanted to touch on. I'm curious your perspective on regulation. I mean, obviously it's coming, but I'd be interested to know kind of what you think about it, like what good regulation would look like.
If I only knew, right? that's a good discussion. I think being in Europe, one of the things that I needed to learn is that how can you use regulation in order to build value systems of a society into your AI deployments? And that can be a good thing. I think the regulation needs to address the realities of AI as being an experimental technology, and we need to deal with these uncertainties, but also make sure that we are not opening the door for extreme abuses and give people and consumers the right to protest, right? How to exactly build this regulation, I don't know. I think that what I appreciate about the regulatory frameworks that we have in the EU is that we are more willing to iterate on regulations, which is good. Like, we make a draft, we see how it's being in practice. Some things work, some things don't work. We try to adjust. Classic example, GDPR and the cookie banners. I don't know how many cookies you have to click away. It's really annoying, and people got it. And now we're trying to figure out how to build a regulation that we don't have to do this anymore. But it takes time. And I think it's a process. And I think as a technologist, you're actually building software for humans, right? You don't build technology for your own sake. You're building in order to make something better, to do something better, to make somebody's life better.
But I guess specifically, what's like a regulation that you would like to see happen?
What I would like to see happen is to allow for ML models to have a sandbox environment where you can say, like, I can do tests on real world scenarios, where I can collect data in the real world in a given risk frame. And then you can get risk certifications that are going up, where you say, like, okay, I did my first test that was an exposure of, I don't know, $1 million in risk, right? Just arbitrary number. Don't take them for like fixed prices. A certifier says, like, okay, that's great. Now we can go to the next iteration phase. And then you build up this risk where you can say, like, a certifier is willing to back you up on insurance for a given risk factor. Because only then can you actually use these experimental technologies to go out into the real world. Because right now, hands are often bound, right? Like by data privacy issues, by copyright issues, by security concerns. And so the regulatory uncertainties around that, for especially for a startup that builds ML, is really, really high. And so I would like to see having protected environments where you are allowed to test things within a certain box. And I think that would be a good regulation, because the consumer can slowly gather trust and can see what it can do in the real world. You start to see curiosity, and you have it under control to a certain extent, because you know if the company does something wrong, it's going to get penalized, and that's bad for the company. So I think that would be a good regulation that I would like to see in this form or another.
I saw you also wrote on ML and environmental impact, and that's something I care about a lot and have looked at. What's your thoughts there? I mean, do you feel like people should be finding ways to train models with less compute? I mean, how do you reconcile the fact that you're also doing model training in your day-to-day job?
It's a complicated question. On the one hand, big models and ML models are really powerful and important. On the other hand, you need to make sure that you're not burning up the planet with them, right? So my stance on this is, let's reuse those models as much as you can. fine-tuning, zero-shot learning. Once you train them and really invested in that money, let's make sure that this cost, this carbon footprint, and the monetary stuff amortizes. And that's what we're currently seeing, right? Like there's a lot of interest in training these big models, pre-training them because they fine-tune very well. I just feel like there's too many people who want to just build them from scratch and not figure out like what can we do with the existing ones. And I hope to see a change a little bit in that. Yeah, that's my take on it. Let's not just like shun it, but also like let's be conscious about it.
Makes sense. We always end with two questions, and the second to last question that we always end with is, what's a topic in machine learning that you think is understudied, or what's something that if you had more time, you would love to look into more deeply?
If I had more time, I would probably pull out my physicist hat again and try to understand a lot of the optimization problems within machine learning. There's a whole field that is just ripe for discovery, which is the combination of loss landscapes and optimization problems in deep learning models and a connection to statistical physics. And I think that is a really, really valuable lesson. It can actually help statistical physicists to understand certain things better, but also statistical physics can probably help the ML community to understand much better what's actually happening under the hood. And I would love to contribute to this much more, but that's very far away from what I do every day.
I've seen papers on this topic, and I always find them impenetrable because I think I don't have the background in physics that people are assuming. Can you describe a little bit of what this says to someone like me who maybe knows some of the math and is interested, but doesn't quite follow? Like, is there like an interesting result that you can point to kind of from this analogy?
Physicists typically think in terms of what we call a phase diagram. Classic phase diagram is the different states of water. You have vapor, water, and ice. Similar effects happen in all kinds of other physical materials. And one of the funny things that you can see is that these kind of phase transitions are different, where you go from one phase to another phase, like from liquid to vapor. These kind of transitions also happen in optimization landscapes of machine learning problems. For example, when you tune the number of parameters in a model, you go from the model not being able to optimize at all to the model just suddenly optimizing perfectly. And people describe this as a spin glass to jamming transition, very technical term, but it essentially means like from being like almost quasi frozen state to something that is just very, very, very viscous, and it's a very different physical properties, and you can see those in machine learning models. And so these are the early indications that you can use these kind of method and tools that we developed in statistical physics to understand the dynamics that happen in machine learning models.
Cool.
And ultimately, I think this will help us also train these models much better and at much cheaper cost.
Cool. Well, on a much more practical note, when you think about all the models that you've trained and put into production, what's the hardest piece of that at this moment? Like, what is the biggest challenge from a customer wanting a model to do a particular thing to that thing deployed and working inside of their infrastructure?
I think actually getting the high quality data is really hard, because that's where the customer comes in, and you need to actually pick them up at that point and tell them like it's not just data in and model out, but you need high quality data. We did a project for semantic segmentations of very, very fine detailed mistakes on like huge metal surfaces. These are tiny scratches. You have maybe like 5 or 6 pixels on like a 1,000 by 1,000 pixel image, and you need to find like a loss function for that. And now these images are recorded from various different angles and labeled by different people. So on some images there's a scratch, on some images there's not. Same piece of metal, but you see the scratch and you don't see the scratch. And so helping people understand how to label data, how to bring the data into a quality that the model can actually pick something up is really like the complicated part. I think that's an understudied problem.
How did you actually get the data labeled in this case? I do have some experience with data labeling.
Essentially having an armada of people that use a labeling tool and teach them what to label for and get a huge feedback loop.
Did you build a custom tool for this to find the scratches?
Yeah, we used like open source software. Like I don't know actually which piece we used, and then just adjusted it for that use case in order to make this quick and fast.
Awesome. Well, thank you so much. This is really fun and so many different insights. I love it. Thank you.
Yeah, thank you.
If you're enjoying these interviews and you want to learn more, please click on the link to the show notes in the description where you can find links to all the papers that are mentioned, supplemental material, and a transcription that we work really hard to produce. So check it out.